Welcome to the optical communication course. Today we start with a light emitting diode there, and to understand the phenomena of a how your light is propagating through the diode, we will learn first about the direct recombination and indirect recombination. So direct and indirect recombination, that is about the electron recombination, and because of that recombination of a electron, so that material will emit the photon there. Means emission takes place. So how that emission takes place, that we need to see here. So in a direct band gap type of material, so now these are, we say that they have the conduction band electrons. This one is about a conduction band electrons here, and that for a direct band gap of a material, so here a direct recombination of the electrons and holes takes place here. Okay, so this one is about a direct recombination will be takes place, and that is about electron transition, we say this one. And because of that recombination of electrons and holes here, so then we will get that photon, and that photon of energy, that will be what, because it is about a direct combination, so that's why we'll get that photon of energy E direct is equal to what, hc, or some book they have written that hf, sorry, hv or hf here. V is nothing but the frequency there. Now that is about a direct band gap, and here this one is a momentum. Okay, so we can say that this one is about a momentum in your material there for this direct band gap of a material there. Means we can say that how that electrons and holes are recombined, so that will be depending upon that momentum value, that will be ak. Okay, so now we have mentioned earlier here, so whatever the difference between that particular junction, we have the electrons and holes, okay, for the pn junction, and at that particular junction or at the depletion region, so that recombination of electrons and hole takes place, and because of that recombination, photon emitted, and that photon is of energy that we say hv or hf there. So hf is equal to, if you see that, we can write f is equal to what, c by lambda. We can say that h is equal to c by lambda. H is nothing but a Planck constant. C is a 3 into 10 power 8, that is the light velocity, and lambda is about the emission wavelength for this given particular photon. Now in this particular case, direct recombination takes place there. Means we have the photon, we can say that for a given particular material, so conduction band, and we can say this one a valence band here. Okay, so that conduction band and a valence band both are lie exactly above the maximum energy of the valence band and a conduction band. Okay, if you see that both are lie on the maximum energy, and when they both are alive, at that whatever the momentum of this electron, okay, momentum of this particular energy we have. Okay, so now means that is about a direct recombination. But in the case of a indirect recombination, so we have the conduction band electrons here. This one we say a conduction band electrons, and that is about a valence band. This one we say a valence band. Now, if you consider that in the case of a indirect band, so we have the energy of this particular valence band and a conduction band, and we say that we have the maximum value of this valence band and minimum for this particular conduction band and all. If you consider that at a given particular momentum, it is different here. Okay, so means there will be a difference in the momentum at the value of this particular peak here. So that's why when we say that a recombination of that electron and photon is to be taken place, so in that case, so here in general we say this may from that electrons we say here, that is about a photon of energy we have, and because of that at this particular direct recombination we can say that a photon of energy is emitted. But in the case of indirect recombination, that path we need to flow, and in the case of indirect recombination, so direct electron and holes not recombine here. So conduction band, if we see that a conduction band minimum and this one is valence band maximum, and that energy level occurs at the different value of the momentum. Okay, see that. Here we can say that we have the conduction band of electrons, that is about the energy level for this conduction band, and we can say that energy level for this valence band. So here the conduction band minimum and valence band maximum, that energy levels at that particular momentum. Okay, if you see that maximum and a minimum occurs at the different values of the momentum. So means band to band recombination, that is not takes place here in the indirect band. Okay, because they have the different momentum. But in the case of a direct level here, we have the conduction band minimum and valence band maximum. So direct to direct recombination takes place at this particular band energy level. Okay, but again it will emit some photon of a energy, and that photon of a energy, that will be depending upon photon energy, that will be depending upon that HV is equal to what, indirect one minus the photon of a energy. And here in the case of photon of energy, that will be this this one is about EPH here, and here we have a photon of energy, that will be what, HV plus HV is equal to what, indirect one plus EPH, that will be the photon. So light emitting diode, if you consider, if you take an example, or if you use a light emitting diode, that is made up of a direct band of a recombination. So now what are those material that will produce a direct band of a recombination? So that materials are nothing but what, a semiconductor material, that will be a gallium GaSb here, or gallium arsenic here, and iron indium As here. Now these are about the material, and for this particular semiconductor material, if you consider that band gap of energy is about a 0.73. This one is a band gap of energy. Here we have the material, and here the band gap of energy is about a 1.43. We have the 0.35 energy band gap, and here we have the energy band gap of a 1.8. So for each and every material, they have some recombination rate. So recombination rate is 2.39 into 10 to the power minus 10, and that recombination coefficient is depending upon that what will be the size of this particular material. Okay, and this will recombination rate is depending upon that how, what will be the particular region, in that case will get that recombination there, recombination of electrons and holes takes place. So if you see that recombination rate for the different material is different, it is not necessary we say that that given particular photon emitted by the given material, or that emitted photon directly goes to this optical fiber. Then we should learn about that what will be the any of the optical fiber and how we are designing the light emitting diode structure. So this one is about a direct recombination of a and a indirect recombination of material. Now if you consider that a indirect material, okay, this is about indirect one. So it has a silicon. Silicon it has 1.12 of a energy there, and a recombination rate is about a 1.79 into 10 to the power minus 15 here. Similarly, if you consider that germanium here, and for the germanium, it has a recombination that band gap of energy is about 0.67, and it has the recombination rate is about a 5.25 into 10 to the power minus 4. So that is a given material, direct recombination and indirect material. But if you consider that we are using a gallium arsenide most of the cases here, because of this one is about a direct material, and again a light emitting diode, they are developed not using a single junction homojunction, they are using developed using the heterojunction recombination. So the heterojunctions means what? A different material with a different junction at different particular place. So we'll come to the topic of a light emitting diode. But if you compare it, the light emitting diode with a laser, so what are the various advantages of a LED there, and what are the disadvantages? But if you consider that LED there, the light emitting diode requires a less complex circuitry, because we need a driving circuit for the laser as well as the LED. But if you compare with a LED and a laser, so it has a less complex circuitry we require there, because that when a temperature increases, so we need a circuit, or we need a material, or sorry, we need a driving circuit. They have a no effect on the temperature there. If there will be effect on the temperature or any thermal changes occur, so laser diode doesn't work. But in the case of any variation, thermal variation, that light emitting diode works. But if you compare with in terms of a what will be the optical power and how what will be the efficiency in that case, so then a laser is better there. So now what will be the data rate we can communicate using the light emitting diode? So generally it offers 100 to 200 Mbps. Okay, that is about a data rate. And that data rate, we say that we can use a multi-mode fiber for this. And a optical power that will be given by this light emitting diode, that is in a few microwatts. You can say that your power will be a few microwatts there. So that's why this light emitting diode is used in most of the applications there. And if you see the structure of a light emitting diode, so I'll just show you the structure there, how your light emitting diode structure will be there. That we'll see now. Now, generally, a light emitting diode, if you see that, we say that it has a double heterostructure configuration. Okay, that is about a double heterostructure configuration. But if you consider that, if for a given particular light emitting diode, so how your emission pattern will looks like, then we'll come back to the how your structure is there. So emission pattern means what? How your signal, or how your light is emitted from the light emitting diode. So that's why for the given particular emission pattern, so light emitting diode, it should have the high radiance output. It should have a high radiance output there. There again, the light emitting diode, it should have a fast emission response. Fast emission response means what? For the given particular pulse, so it generate that whatever the light or whatever the photon there, and then it has a high quantum efficiency. Whatever the light emitting diode we say, it should have the high quantum efficiency. Then in the quantum efficiency, we have the internal quantum efficiency and a external quantum efficiency. That will be the total of a quantum efficiency. That internal quantum efficiency means what? Inside a given material, inside a particular junction, that light is emitted. So that's why it is called as a internal quantum efficiency. In the case of external quantum efficiency, whatever the light emitting from this diode, that will be accepted by the fiber. That is about the external quantum efficiency. So if you consider the efficiency, we need to take a part of what will be the external quantum efficiency of the diode. External quantum efficiency is what? For the given particular numerical aperture of a fiber or acceptance angle of a fiber, your light is emitted inside or light is propagating through the fiber there. That is about the a quantum efficiency of the given material. Then we say that for the given emission pattern, we say that we require the high radiance of the output. But when we will get that high radiance of the output, so that the combination of the material at the given junction and that your light emitted by this device, and that will be in a given particular solid angle. So we can find out if when we'll get that high output power level, okay, at what particular place or what particular region we are getting the output power there. In the case of emission response times, so in the case we can say that generally we say that if whatever the current is propagating, when we apply that current to the light emitting diode, then it will start emitting the photon of energy there. Now, how your device response, your light emitting diode response for this particular current pulse there, that we need to learn. So then to achieve this particular high radiance value or a high quantum efficiency there, so then what we require? We require a junction of this particular material. It will produces that high radiance output or that particular emission response to be a fast. So means what? Means we say that a recombination rate. Recombination rate means what? Electrons and hole recombination rate. But again, there are two types of recombination. We say that will be what? A radiative recombination and a non-radiative recombination. In the case of a radiative recombination, when electron hole pair at the particular junction match, okay, at that particular region came across, okay, when the combination of electrons and hole takes place, so then it will emit the photon of energy. It will emit the photon of energy that will be HV. So that is called as a radiative recombination. So when it emits the photon of energy, so we'll get that a radiation output or high radiance output. But in the case of a non-radiative recombination, in that case, what happens? That recombination of that electrons and holes takes place inside the whatever the material there. But what happens? It not emits the photon of energy. Recombination takes place at that particular junction. Recombination of electrons and hole takes place at that particular junction. But that recombination will generate the heat. It not emit the photon of energy. So now it generate a heat means what? That whatever the emission takes place, that will be absorbed inside the given material. Means recombination in that region is takes place there at a particular junction. But whatever the emission takes place from this device, it will be absorbed as a heat. Okay, it will be absorbed inside the material. So that's why that is nothing but a recombination rate or recombination due to the recombination, it will be generated there. But in the case of radiative recombination, it will emit as a photon of a energy there. So we use a material in such a way that we'll get that a high radiance output. So that's why we have the various configuration of LEDs, and that LEDs various configuration means what? How your junction based on this recombination there takes place there. So that's why we have the two categories there. One is about a homojunction. Okay, that is about first category of a homojunction, and we have the heterojunction there. Means to achieve that particular recombination in that particular junction, or you can say that to achieve the particular radiance in that particular junction, so we can develop or we can describe the structure of a LED based on the junction there. So it is about a homojunction and a heterojunction. It will be heterojunction will be a single heterojunction or a double heterojunction. You can say or here. Okay, single junction or a double heterojunction. But out of this, homojunction means what? A same material we say. Heterojunction is about the different kind of a material. So to achieve that high radiance output, fast emission response time, and high quantum efficiency, so most of the people they are using the double heterojunction device. Because double heterojunction means what? They have a two different layers on each side of that active region. Active region means what? For a given particular junction. So this one is about a depletion region we say, and this one is nothing but the active region there. Okay, this one junction at this particular depletion width, we whatever the depletion width of this particular junction we say, this one is nothing but the active region. So in that particular double heterojunction layer, we say that they have the two different layers on each side of that particular active region there. So now how these heterojunctions are configured here. So we should know that one particular double heterojunction structure here. Now in this case of a double heterojunction structure, this one is a metal contact. This diagram is taken from the book, that is a caser here, and most of the material we are using that caser and a scenario. This is about a metal contact. Then we have a N-type gallium arsenide here substrate. This one we say a N-type gallium arsenide substrate there. This one we say that is about a N-type gallium arsenide, that is 1 minus X, then Al, X, and a arsenide. And this one is about a recombination region. This recombination region is again a N-type gallium arsenide 1 minus X. That X we'll see later, okay? Al, then As. Then a P-type, okay? It's again the same here. So now this material is about, you can say that, light guidance and a carrier confinement. This region is about a recombination region, that is about a zero point 0.3 micrometer of a length, and this region is about a light guiding and a carrier confinement. In these two regions, these are the guiding your photon in this particular recombination region, and this one is about a metal contact improvement layer for this p type here. Now if you consider this, that's why we can say that is about a double heterojunction. Now this one we say energy gap of for the given material. This one we have a light guiding material, and this one we recombination region we have the conduction band and a valence band here. So electron hole recombination takes place at this, sorry, electron and hole recombination takes place at this particular place. So that's why it emits a photon of HV is equal to 820 nanometer. Now that gap of energy 1.51 electron volt here. So this one is about the active region. It generates that recombination. Now in the case of a refractive index for the given region, so for the given region, they have the different values of the refractive index. So for this given material, if you consider that guiding material, it has a low refractive index, it has the high refractive index. Active region has the high refractive index. So whichever the light is emitting from this particular region, that will not propagate in this particular region. So that's why it will be, you can say that it will be radiated. So there are the two types of a combination. So if you see that we have the region that is about active region, or a, whatever the layers we say. So based on that, for the LED structure, there are the two types of a configurations we are using. Generally, a LED configuration that is about for a given particular fiber, one is about a surface emitting LED, and another is about a edge emitting LED. Now, in the case of a surface emitting LED, this one is about the edge emitting LED. There are the two types of configurations used in the light emitting diode there. So we'll see that one by one here for the surface emitting LED. So this one a active region for the surface emitting LED. This one is about the active region, and that other component is nothing but this one is about heat sink, metallization. This one is about a isolation layer, and here we have the circular metal contact. That is a, and then this one we can say at the nearer to this active region, a fiber is connected there. So at the manufacturing itself, so nearest to the active region, that fiber is connected there. And then fiber is coupled here. So whenever you connect to the fiber, so you can connect another fiber to be here, and then your light is propagating through it. So at the time of a manufacturing here, that a fiber is connected. If you consider that a active region, the plane of this particular active region that will be perpendicular here. Now, if you see that, so that we see that we have this plane of this particular active region that will be perpendicular to this particular fiber here, fiber axis. And this configuration, if you consider that active regions we have connected, or it will deployed on the given particular substrate, and then and that particular substrate we say that a fiber is cemented in this particular substrate, so that whatever the light emitting from this particular active region, all the light will be accepted by this particular fiber. That is theoretical we are. Practically it is different. Whatever the light is emitted by this active region, that will be all the light is to be accepted by this fiber there. Okay, that is about a theoretical. So generally, if you consider that a how your emission of this particular light is takes place there, that's why we have the a circular edged wall here. So emission of this particular light or the particular surface emitter, we say it is about the circular active area here. Okay, this is about a circular active area we have. And that circular active area, it has a diameter of a 50 micrometer. It has a diameter of a 50 micrometer, and it has a 2.5 micrometer thickness. Okay, you just remember that how much is the diameter for this particular circular area and all. And the emission pattern, generally we say that is about the isotropic radiation is takes place. And in isotropic radiation, that is about a radiation, or we can say that is about the emission. That will be a isotropic here. And it has a 120 degree of a beam width. It has a 120 degree of a beam width. So we'll come to the top topic, how your radiation takes place. Means for a given particular source, we'll get that radiation pattern will be a likewise. And it has a 120 degree of a beam width, just like we say that a maximum point or this point is nothing but this one is the maximum here, and this is about the 3 point or half power point, and whichever the theta is there in between that theta is nothing but a 120 degree. Okay, just I am saying. So it is isotropic means what? It radiates the signal in all the directions in one plane. It radiates the signal in all directions in one plane. But it has the isotropic radiation with a beam width of a 120 degree. Means radiation takes place. But that acceptance angle of a fiber, if you compare, so it will not be, we say that that will be of a 120 degree there. So generally this pattern we say it is about a Lambertian pattern, and it has the maximum radiation at this particular place. Here we can say that a maximum radiation takes place, or at this particular place your output will be very bright. But isotropic radiation means what? If you look from any direction, it looks like that it radiates a signal. It radiates a signal in all the direction, and it has a same intensity all over the region. If you look from the any other direction, just like a light, if you see that, okay, so it radiates in all the directions. But if you consider the intensity, so it has the intensity, maximum intensity in the given region there at this particular maximum here. So that's why we consider that when we talk about that how much is the power, so we need to talk about that how much is the power we are getting maximum with respect to cos of a theta value. And if that theta changes, so your power reduces there. Okay, so means if you, here is a cos of theta, theta is supposed to be max whatever the value we are according to the angle, so it will be gradually reduces the cos of theta. So means we say that here we are getting the maximum value, and the theta changes, so power decreases. Okay, means intensity of this light will be decreases here. So that is about a light emitting diode, and if you see that a active junction here for this light emitting diode, so it produces a light in all the directions. So that's why it is called as, we can say that is about the incoherent light. So we can say that light emitting from this, it is nothing but a incoherent, and it has a two guided layer. It has a two guiding layer. So this is about one guiding layer and another guiding layer, and this one is about the recombination region. And this guiding layer, if you see that, they have the low refractive index. Guiding layer, they have the low refractive index. And surrounding to this one is about the active region, and it has that active region, it has the higher refractive index. Okay, so that is about it. So that's why that radiation takes place in this particular active region here. And then we say that a fiber diameter is of a 50 micrometer or a nearly 50 to 100 micrometer, we say, and we have this a contact to this particular diode or a contact strips for this edge emitter is about a 50 to 70 micrometer wide. Okay, that is about a contact strip for this particular diode. So this length of this particular active region, we can increase or decrease. Generally, we say that a active region of a diameter 50 micrometer. So we can increase that the length of this particular active region from this 100 to 150 of a micrometer there. So that's why we are getting that if we increase this length, so we'll get that a radiation, more radiation. Okay, but here in the case, it is about a 50 micrometer there. So, so whatever the emission takes place in this particular active region, it will be isotropic one, means all the direction. So that is about a surface. But if you consider that a age emitting LED there, so that age emitter, if you consider that it radiate the light only in the one direction there. Okay, so it is about a, we have this a double heterojunction layer. This one is about a double heterojunction layer. This one is about a substrate. On a substrate, that double heterojunction layer is there, and this one is about your active region. Now the same we say, that is about the refractive index for this uh, whatever the guiding layers we have, that the lower. Okay, this one is about a refractive index for guiding layer, that will be lower than this active region there. So means higher active region. And then because it emits the light through the edge of this particular fiber, so that's why we can connect a fiber easily to this particular light emitting diode. Okay, edge emitting light emitting diode. And it has a fiber core diameter. Generally, we say that a 50 to 100 micrometer of it diode there, and a contact tips is about the 100 to 150 micrometer. That is about the length of this particular active region. And a contact, if you consider that, that will be nearly about 50 to 100 meter, means nearly about a 50 to 70 micrometer. That will be the contact strip for this particular edge emitter. Now, so here we have the strip contacts to this particular active region. Okay, so this one is about active region defines. These are about the strip contact. And these two layers, we say that is about a guiding layer. It has a low refractive index. And this one heat sink, metallization contact for the electrical contacts and all. And the name is about edge emitting. Why it is edge emitting? Because the edge emission pattern for this edge emitting diode, it is a highly directional. Okay, it will be highly directional than the surface emitting LED. So that's why if you see that emission pattern here in this one direction, that is about the emission pattern there. And we can connect a fiber to this here, and we can say that this one is about a half power beamwidth for this radiation plane perpendicular to this particular junction. That is about a theta 1 here, and this one is about a we can say that's about a parallel one. This one is perpendicular one, this one is about a parallel one, and we are getting that radiation pattern from this light emitting diode. That will be a Lambertian pattern in a highly directional. Now we say that a material we are using, that is a, we say that 1 minus x and all, and that x is nothing but that, depending upon that what will be the band gap of material we are using and what will be the alloy, and according to that x we can vary. So generally x is the value of a 0.08, it is to be used, so that we'll get that a high radiation output there. If you consider that a given particular material, that we have the diagram here. So for the direct band gap of energy, so in that case, x value for this AL will be from the 0 to 0.5, and this one is about the energy band gap. Okay, this is about a energy band gap. That is about a EVM. For the direct band gap, x fraction will changes for this AL, so we'll get that particular energy. Okay, so that's why x is the factor that is used for the given particular energy here. Next is about the radiation pattern. So radiation pattern, if you consider that for the surface emitting LED and the edge emitting LED, this one is about your wavelength, and here we have the maximum peak occurs at this 1.3000 micrometer. Means what? 1300 nanometer. You can say that 1300 nanometer. Here we have the peak here. Okay, approximately at this particular place, or 1350 nanometer. Okay, this one. Generally, you can say it is about a 130 or 130. Okay, likewise, we can say that about a nanometer peak is available here. So this one is about the radiation pattern, or we can say that a spectral emission pattern of this light emitting diode. So edge emitting LED, this one is about edge emitting LED. This one is about a surface dash line. This one is about a surface emitting LED. And if you see that a surface emitting LED, it has a spectral width of a 125 nanometer. And for the edge emitting LED, it has a spectral width that is about sigma lambda is about a 75 nanometer. Now, what do you mean by this particular spectral width? The spectral width means for a given particular light emitting diode, we have the radiation pattern we are getting for the given particular spectrum. Okay, and it is about a spectral width will tell you that radiation of this particular 1300 nanometer, that will be around that 75 nano. Suppose we say that is about, for example, we take a sigma lambda is about a 50 nanometer. Okay, that will be easiest example. And we say that a peak occur at 1300 nanometer. That is about a peak now. Means what we can say that at a 1275 to 1325, this is about the band here, we'll get that irradiation. Okay, radiation intensity. But the peak is maximum peak is at the 130, and that is about a spectral width for the given source. Okay, that is about a radiation for the given particular source. So if you consider this different material or a material combination, so then spectral width will be changed. So we say that a energy is propagating, or we can say that a band gap of energy is nothing but we say Hv is equal to what?